Today we will talk about the metal carbon bond, which is formed between a metal and an alkyl group. By an alkyl group, I wish to include aryl moieties, alkyl moieties such as ethyl, methyl or propyl, and other systems like benzyls and allyls and vinyls. So, we will group all of these moieties together as alkyls. So, if you have an M-R bond, what would be the chemistry of that bond and how does it behave? These are the things that we are going to talk about today. First of all, we have to take care of the electron count, and in the neutral method that we talked about earlier, the R group is actually an radical. So, it is similar to what I would call as a chlorine radical. So, it is similar to the chlorine radical and it would be a 1 electron donor. When it forms a metal alkyl bond, we actually take 1 electron from the metal and hence form the M-R bond. So, this would be the neutral method. In the anionic method, we actually consider the R as R minus. This is purely for convenience, because carbon is in general more electronegative than the metal. So, we consider R as R minus, and then it would be a 2 electron donor, and it would have a negative charge. So, these two aspects need to be kept in mind as we discuss the chemistry of the metal alkyl bond. And initially, I wish to look at some of the preparative methods that are available for us to generate this metal alkyl bond. When we talk about metal alkyls, it would be ideal if we look at some of the methods that permit us to make the metal alkyl bond or generate the metal alkyl bond directly from the organic compound. The most easy method is to use an organic halide, as I have pictured here, and react it with a metal atom, any metal atom which is reasonably reactive. By reactive, I mean it has to be electropositive enough, so that the Mx which is formed has got a very stable bond, and the formation of Mx actually drives this reaction from the left side to the right side. So, if you take the reaction between alkyl bromide like butyl bromide, this is probably one of the most familiar and most common reagents that is used in organometallic chemistry. So, if you treat butyl bromide with magnesium, one ends up with butyl magnesium bromide, which is C4H9 MgBr. And this butyl magnesium bromide, although we write it in this particular fashion, is not necessarily the same in solution. It is in equilibrium, as we shall see shortly, with other species, but nevertheless it is convenient to talk about it as if it is butyl magnesium bromide in this fashion. There is a different method that we can use in order to activate the metal. As I told you earlier, it is important to use a very reactive metal. In the earlier instance, we use magnesium, and that is a very reactive metal. We can also use an alloy or a metal that will promote this reaction, but not itself participate in the reaction. One very good example is the alloy that is formed between sodium and lead. So, sodium and lead form an alloy which is NaPb, and this NaPb ligand an APB alloy will react with ethyl chloride to form tetraethyl lead. And this tetraethyl lead, when it is formed, it also generates sodium chloride. Since sodium chloride is a molecule which generates a lot of heat, it is a very stable molecule. This reaction goes from left to right and forms tetraethyl lead. The bond between the ethyl group and the lead itself is not as strong as in the other case, where we had magnesium and ethyl or magnesium and butyl forming a bond. But in spite of that, this reaction is driven in the forward direction because of the formation of sodium chloride, which is a very stable molecule. So, if you do not have a very reactive metal, we should use a very reactive organic compound. An example for such a reactive organic compound, I have taken cyclopentadiene. Now, you know that cyclopentadiene is easily ionized as H plus and C5H5 minus, and that is because the C5H5 minus ion is aromatic and could be written with a set of delocalized bonds in this fashion with a negative charge. So, that is a very stable system, and so the formation of this sodium organometallic, which I have pictured here, is very easy by directly reacting sodium with cyclopentadiene. To make sodium more reactive, one normally converts this into sodium sand, and this is purely a matter of convenience. One can heat the sodium and shake it up vigorously, so that it forms fine droplets, and these fine droplets of molten sodium are extremely reactive, and they react with C5H6 and liberate hydrogen and form this organometallic compound C5H5Na. Yet another method of making an organometallic compound, starting with a reactive organic compound, where there is an active CH. So, in both of these cases, the presence of an active CH is what is important. Here we have a CH group next to a ketone, and that is enolizable. So, acetone has an active CH bond next to the CO group, and that is activated, and it can be converted into an organometallic compound where there is a CHG bond, and one needs to use this bis trimethylsilyl nitrogen compound, tris trimethylsilyl compound, which is attached to mercury, and that is already a mercury 2 plus compound, but it exchanges with this active hydrogen in order to produce a carbon mercury bond. So, this is yet another way of making a metal alkyl bond fairly readily. These examples illustrate that you have a tendency for a C minus interacting with a metal atom, and that is the basis for forming these metal alkyl species. Here there is a variation in this particular projection that I am showing you. You can use a metal carboxylate, and if you heat the metal carboxylate, because of the elimination of carbon dioxide, you will form a metal alkyl compound, and this is convenient because there are instances where you can generate metal alkyls which are otherwise difficult to make. Here is a mercury compound with a trifluoromethyl group attached to the mercury. So, it is bis trifluoromethyl mercury that is formed, and that is here bis trifluoromethyl mercury. because of the liberation of carbon dioxide, this reaction is again thermodynamically favorable and it is driven to the right side, and you have very good yields of a dialkyl mercury compound being formed. The reactions that we have pictured in this projection are all driven from left to right because of elimination of a volatile molecule like carbon dioxide, or in the last instance it is dinitrogen, and dinitrogen elimination leads to the formation of a aryl mercury bond in this instance, and that is the elimination of nitrogen from arene diazonium salt. So, this is ArN2 plus Cl minus, and this molecule merely is transferring an aryl group to the mercury, and you have the formation of a mercury 2 plus compound. So, during the process you also have an oxidation of the mercury from 1 plus to 2 plus. So, let us proceed further. The most common method of making organometallic compounds, however, is a reaction called a transmetallation. In this instance, I have pictured a metal which is exchanging with position with another metal in an alkyl compound. So, you already have a metal alkyl bond, and you are merely transferring this R group from this position on to this other metal. And so, MR is formed and this M dash is liberated. Once again, for a transmetallation reaction, you should have the thermodynamics right, and in the example that I have given here, you are transferring the metal from mercury to zinc, and because the zinc methyl bond is stronger, you have this reaction going from left to right, and dimethyl zinc is formed in this process. And mercury is usually eliminated as liquid mercury, which comes out from the reaction and can be easily removed, and you can have very pure dimethyl zinc in this reaction. Once again, transmetallation is a process which you can use if you have a metal alkyl bond which is formed from a direct reaction. In this particular reaction or transparency that I am showing here, you react a methyl lithium. The methyl lithium is formed from methyl bromide and lithium, and then once you have this metal alkyl, you can transfer it to a less electronegative, less electropositive element like antimony, and you form an organometallic compound which is not possible to, it is not possible to generate this antimony compound directly from a reaction of methyl bromide and antimony, but by this indirect method you first convert it to methyl lithium and then transfer the methyl group from the lithium onto the antimony atom. Here is another example which is slightly different from what we have discussed earlier, and here I am going to transfer a butyl group. I am going to transfer the butyl group to a halogen and a phenyl group to the lithium, and because the phenyl lithium is what has a better phenyl lithium interaction compared to the butyl, this reaction proceeds from left to right and you have elimination of butyl halide. Now, it is very difficult to break carbon fluorine bonds. It is a very strong bond and it is not possible to break it. So, you would have to use either a bromine or an iodine in order for this reaction to proceed fairly readily. So, this reaction works if you have phenyl bromide or phenyl iodide, but it will not work with CF and it will be very sluggish and if not impossible with carbon chlorine also. So, chlorobenzene and fluorobenzene are not good substrates, but bromo and iodobenzenes are good substrates for this particular transmetallation that we have carried out. So, organotin compounds are extremely important in the industry. It is also commonly used in the laboratory, and here is a transmetallation where we are carrying out a transmetallation between magnesium and tin, and the group that is transferred is vinyl. So, one would have to generate the species, one can generate the species from vinyl bromide and magnesium using the reaction that we talked about earlier. You would end up with vinyl magnesium bromide, which is again readily made in the laboratory, and it can be transferred to the tin. So, the vinyl group is transferred to the tin, and tetravinyl tin is formed in this process, and you can, because we are eliminating two very stable molecules or salts in this process, we have formation of this molecule tetravinyl tin very readily. Tin is a special example because one can readily do transmetallation between one tin atom to the other. Here I have pictured for you a metathesis reaction. Metathesis purely means a change of place. Transmetallation is also a change of place, where the alkyl group changes place from one metal atom to the other. So, if you react R3-SnCl with R-SnCl3, both are tin 4 species. Both are tin 4 species, and you are merely exchanging an R group from one tin to the other. That tells you that because you are not having a thermodynamic difference in the R-Sn bond, this must be due to the fact that you are forming a set of compounds which are, all of them are almost isoenergetic, and probably its entropy, the equilibrium is entropy driven. And it is possible to carry out this reaction at very good yields and with at high temperature. And R2-SnCl2 is an important intermediate which is used in the stabilization of PVC. What happens is you can use tin chlorides, tin alkyls as molecules which will absorb hydrochloric HCl that is evolved during the formation of making of PVC. You can also use it, R2-SnCl2 is also used for the stabilization or the formation of SnO2 on glass, and tin oxide coated glass is a special glass which is very important in the industry as well. So, R2-SnCl2 and R2-SN are molecules which are reasonably accessible and fairly important in the literature. So, Mn2CO10 is a molecule which we have already encountered in the carbonyl chemistry. This is easily reduced because you have a manganese-manganese bond, Mn-Mn bond, and this Mn-Mn bond can be converted to anionic species, can be broken and converted to an anionic species, which is also an 18 electron species. So, sodium salt of MnCO5 minus is readily formed in this process, and this MnCO5 minus is a nucleophile, and it can react with methyl bromide. It can react with methyl bromide and generate a MeMnCO5 species. So, each one of these lines is equivalent to a carbon monoxide. So, that is actually equivalent to a carbon monoxide attached to the metal, and we have a methyl manganese bond being formed, and you also have in this process sodium bromide eliminated. So, this is a reaction which can be carried out if you have an anionic metal species, and it is not uncommon in organometallic chemistry to have anionic species, because the negative charge is in fact stabilized by the 5 carbon monoxides which are present on the manganese. They can accept electron density and stabilize the negative charge on the metal. So, we have looked at a variety of preparative methods for the metal carbon bonds. Most of them are the main group compounds that we have considered, and many times it is convenient to make a main group organometallic or metal carbon containing species and then transfer it to a transition metal. In general, it is known that the metal carbon bond is as strong as an Mi bond. A metal iodo bond is a good indicator, the strength of the metal iodo bond is a good indicator of how strong a metal methyl bond would be. That is also similar to what one encounters for the average metal carbonyl bond strength. So, the metal carbonyl bond strength, the metal iodo bond strength and the metal methyl bond strength all fall in the same range. However, in a particular metal system, it is found that the metal hydride bond is much stronger, and that is what I have pictured here. The metal hydride bond is much stronger than the metal phenyl bond. So, if an aryl group is attached to the metal, then that is more easily broken compared to the metal hydride, and that in turn is stronger than a metal methyl and a metal metal bond. So, this is the order in which you have bond strengths in a set of alkyl groups. So, if you vary the alkyl group, you find that the metal aryl group is much stronger than a metal alkyl group. So, here I have given some representative values for the species which we just encountered, and that is HMnCO5 has got a bond strength of 213 kilojoules per mole, whereas the metal carbonyl species that we just encountered in the previous slide is worth about 153 kilojoules per mole. So, you have bond strengths that vary from 200 to 100 kilojoules per mole. And so, the metal carbon chemistry is quite important, and it is often encountered in organometallic chemistry, and is probably the only group which has got purely sigma interactions between the metal and the alkyl group. We will discuss this in greater detail in a later lecture. We considered what happens when you change the alkyl group. In this particular transparency, I have shown you what would happen if you change the metal. If you moved from a manganese methyl group to a rhenium methyl group, usually the bond strength increases. So, this is a 3D element, and if you go down the group manganese, technetium and rhenium, so you end up with a very strong metal alkyl bond strength. So, this seems to be a general phenomenon. If you go from titanium to zirconium, once again you have a bond strength increase of nearly 50%. So, from 240 kilojoules per mole, you end up with 380 kilojoules per mole. So, it is generally known that you have much stronger bond strengths if you go from one metal to another, which is lower down in the periodic table. So, the trends in metal carbon bond strengths, at least in transition metals, follow this order. It is interesting that the same order is not followed if you go to the main group chemistry. So, in main group chemistry, the metal carbon bond strength or the element carbon bond strength, if you want to call it, that keeps decreasing as you go down the group. So, here are some examples that I have shown you. So, if you take silicon methyl bond, it is about 300 kilojoules per mole, and if you make the corresponding germanium methyl bond, it goes down to 249 kilojoules per mole. So, here we are talking about GeMe4 and SiMe4, and we are talking about the average bond strength which is required for breaking the 4 methyl groups together, and then we take the average for for all 4 methyl germanium bonds, and we get 249 kilojoules per mole. Similarly, tin goes down to 218, tin goes down further, and lead forms the weakest bond, which is 153 kilojoules per mole. So, in general, if you go down the group, the bond strength seems to come down, decreases as you go down the group. And this is uniformly observed for all compounds which are organometallic compounds of the main group. Here I have zinc, cadmium and mercury, and also falls in the same trend, has the same trend. You have a decrease in the bond strength as you go down from zinc to mercury. So, this difference between the main group and the transition metal chemistry is often observed in many properties, including bond length changes, bond strength changes, and this is something which we have to look at from the theoretical point of view and see why is it that these bond strengths vary in the way they do. So, let me now proceed to some of the trends that we some of the properties of the alkyl metal bond, and we will discuss this the main group chemistry a little bit, and before we proceed to the transition metal chemistry. In general, what we found was that as you go down the group, at least in main group chemistry, the bond strength decreases. And you also know that the electropositive character of the metal increases as you go down the group. So, the red arrow is connected to what we have shown here, the electropositive nature of the metal, and that seems to increase as you go down the group, and the electronegativity of course changes in the opposite direction. So, beryllium is the most electronegative species in this group of elements that I have pictured for you on the right side, and the reactivity of the metal alkyl species, in this case R2M, the reactivity of R2M is such that it becomes more reactive as you go down the group. So, as you go down the group, it behaves more and more like R minus, and because it is R minus, the reactivity increases as you increase the electropositive character of the metal. So, remember that although we write the metal alkyl species as R2M, it is still not a saturated species. If you remember the electron counting that we did, R gives 1 electron in the neutral method, and so if you have 2 of these, you cannot have a totally filled set of orbitals, because 2 NP orbitals will be vacant if we occupied the S and the P orbitals with the 2 electrons that came from the R groups, and the metal itself has got 2 electrons in the group 2. So, you will only have total of 4 electrons and 2 p orbitals or 2 NP orbitals will be vacant. Usually, this means that you need some other species to coordinate to the metal and stabilize the metal, and the stabilization is usually carried out with a solvent or an added ligand. The solvent is the solvent in which the species is formed initially. It has to be an ether or an amine in order to stabilize the incipiently formed metal alkyl species. If there is better coordination, there is better stabilization, but then the reactivity of the metal alkyl species is poor. So, you have the familiar change between coordination, stabilization and reactivity. The more reactive the species, the poorer it is coordinated, and vice versa. So, in general, diethyl ether is a very convenient ligand. It also is a convenient solvent which is used in the preparation of Grignards, and so it is the RMGX is usually coordinated with diethyl ether. And if you want to make unsolvated Grignard reagents, these are extremely difficult to make, and the less you coordinate the Grignard, the more reactive it becomes. But there is also a trend in the Rx group. When you make Ri, then the Rx tends to be more reactive and the Grignard is more readily formed. So, here we are not talking about the reactivity of the RMGX, we are talking about the facility with which RMGX is formed. For a fluoride, it is very difficult to form a Grignard reagent, whereas with an iodide, it is very easy to form the Grignard reagent. And with fluorine, as I said, it is almost impossible to break the CF bond, and that is the reason why it becomes so difficult to make the fluoro Grignard. Now, let us take a look at a little bit about Grignard reagents and the problems associated with Grignard reagents. Usually, the preparation is a bit difficult because you need very clear, very clean magnesium surface, and the surface is usually contaminated with an oxide layer, and you need to clean it up with an acid wash and then subsequently wash it with a solvent which will not oxidize it, and a solvent which will coordinate to the incipient Grignard which is formed. And as I have told you earlier, the X group affects the reactivity of the Grignard reagent as well. So, now let us look at the other problems which are associated with Grignards. I had mentioned this earlier, but although we write RMGX as the species which is there in solution, this is the species which we usually write as the species available in solution, but it is in equilibrium with R2M and MX2, and this makes the reactivity of the species change in the presence of added MX2. You can change the reactivity of the solution by adding some MX2 to the solution. So, you can change this equilibrium position by adding one of these compounds, and you can change the reactivity of the species. In many cases, people try to remove the MX2 from the solution, so that more reactive species can be obtained. And although this is possible, it is possible to make a Grignard reagent in an alkane solution, where the MX2 has precipitated out. It is in general more reactive, and because it is more reactive, it tends to decompose very readily. And so, its shelf life goes down as you remove the ether and replace it with an alkane. So, there is another complication that is associated with Grignard reagents, and that is the fact that you can observe radical type reactions in Grignard reactions sometimes. And once again, this is associated with the equilibrium that is present in solution. RMGX is the usual species that we think about as being present. RMGX is the species that is present, but it can dissociate or be in equilibrium with a radical species R dot. So, this R dot can accept an electron from MGX and form Rx minus as well, and Mg plus dot. So, a variety of species can be present in solution. This is in general, this is not a common occurrence, but it has been noticed that if you have radical species in solution, the radical character of the Grignard reagent is enhanced, and you can in fact promote radical reactions by adding species like oxygen. Then you would induce radical like reactivity, and the radical can be trapped. So, R dot is a radical that is generated in solution and can be trapped with a tempo, and an OR bond is then formed. So, OR bond is formed because the R dot reacts with tempo to form the species. So, let us proceed further. I talked about Grignard reagents being one of the most common reagents, and it is easy to make it in the laboratory. But some species are difficult, some alkyl bromides or halides are difficult to make, and so one has to start with the alkyl chloride or an alkyl fluoride, and in that case it is very difficult to make the Grignard reagent. So, it was discovered by Rieke that the magnesium, which is usually used as a powder, or magnesium is used as a metal ribbon, this magnesium can be activated further by a special process. And this very reactive magnesium is generated in situ by reducing the magnesium chloride with potassium and THF. When at the reflux temperature of THF, potassium actually dissolves and or melts and forms a metal globule, and that metal globule reduces the magnesium chloride and forms a black magnesium powder, and this black magnesium powder that is formed is extremely reactive. So, this is a pyrophoric powder that is formed by reduction of magnesium from magnesium 2 plus using very reactive potassium. So, this is called Rieke magnesium, and it has some very interesting properties apart from the fact that it is not a shiny metal, but it is a black powder and it can catch fire when you expose it to air. It is so reactive that THF, tetrahydrofuran, which is a common solvent used when you make Grignards, can be cleaved. So, even the CO bond can be ruptured in the presence of Rieke magnesium. So, Rieke magnesium has a tendency to break the CO bond and form the 6-membered metallocycle. So, some reactions of Rieke magnesium can be in fact disadvantageous. If you have THF and you have to reflux the solution, then you can end up with side products because of the formation of such a metallocycle. This Rieke magnesium is so reactive that it can complex to a double bond. Although the structure of this species is not completely understood, it can form a complex species with magnesium. In the case of anthracene, the central ring is less aromatic, and so it can be complex to this Rieke magnesium in such a fashion that there are 2 carbon magnesium bonds formed in the process, and you can have 3 THF molecules which are coordinated to the magnesium, and the oxygen of THF coordinates to the magnesium in such a fashion, and this coordination stabilizes the magnesium, which is now complex to the naphthalene moiety. So, this reactive magnesium can be used in a variety of ways. One very interesting use that has been proposed is the fact that it can be used as a catalyst for the storage of hydrogen. Magnesium itself can adsorb or chemisorb hydrogen and form a species MgH2, and this MgH2 formation is catalyzed by this anthracene complex of magnesium, which I have pictured here. So, this is a catalyst for the formation of MgH2. So, these are some interesting applications of Grignard reagents. Let me now move on a little bit towards about the structures of metal alkyl complexes. They are in fact extremely complex, and some of them have been crystallographically characterized, and I have pictured for you right here the phenyl magnesium complex, which is stabilized by THF. The magnesium is in fact in a tetrahedral array, and it is coordinated with, each phenyl group is coordinated with 2 magnesium atoms, and this complex structure needs a lot of explanation, because you have a fairly difficult bonding situation here, and here is a simpler structure. You can understand this structure more readily. You have 2 ethyl groups which are coordinated to magnesium. So, it is very simply diethyl magnesium, and the magnesium is coordinated to a crown ether here. So, that it forms a very stable complex. So, diethyl magnesium is coordinated to a crown ether, and this structure has been crystallographically characterized. So, here is a picture of a magnesium coordinated to two cyclopentadienyl groups. Most of us are familiar with the structure of ferrocene, which has got two rings of cyclopentadienyl attached to CP rings, and so this is a very familiar structure. Now, if you try to make the analogous magnesium CP2 species, you find that it is no longer similar to ferrocene, but it has got an unsymmetrical coordination to the magnesium. On one side, the ring has got a long metal carbon bond, that is about 2.3 angstroms, and on the other side, it is only 1.39 angstroms. And in this case also the bonding needs a little more explanation, but these structures are more fluxional, and so they are having these unsymmetrical distances only in the solid state. In solution, they would equilibrate to have a more symmetrical structure, as I have pictured here. So, how do you explain these bridge structures that we talked about? In general, it is possible to explain them using what is called 3-centered 2-electron bonding. Suffice it to say at this particular point that if you have a phenyl group with 2 electrons, and you have 2 empty orbitals which are coming from the metal, these are the 2 empty orbitals from the metal, then you will end up with a system which will have 3 orbitals and 2 electrons. And these 3-centered 2-electron bonding interactions are very, very popular or common in main group organometallic chemistry. So, there are only 2 electrons and 3 orbitals which are interacting. Let me now move on to some other species. It is possible in the case of aluminum to react aluminum and RX directly, and in the case of mercury also it is possible to make these molecules with dimethyl mercury and so on. And it is interesting that whereas aluminum would form AlR3 species which are bridged and appear to be reasonably covalent, you have most of the reactions of the alkyl group attached to the aluminum as if R is behaving as an R minus group. So, in many instances you can have R minus behavior for the AlR3 group, whereas in the case of mercury the species is more or less covalent, and what is more surprising is the fact that they have a very large energy difference between the methyl mercury bond. In the first dissociation, it costs about 214 kilojoules per moles, whereas the second bond is only costing about 29 kilojoules per mole when you decompose AgMe. Okay, let me now proceed to transition metal alkyl compounds. Transition metal alkyl compounds are very often easily generated starting with an already made main group organometallic species. In this projection, I have shown you a benzyl magnesium chloride reacting with zirconium tetrachloride, and that makes tetrabenzyl zirconium species. This tetrahedrally coordinated zirconium has got 4 benzyl groups around it, and it is quite stable. And similarly, you can make the titanium species starting with a transmetallation reaction between aluminum and titanium. And since the aluminum chlorine bond is much more stronger than the titanium chlorine bond, so aluminum chlorine bond is formed on this side, So, aluminum chlorine species is formed at the expense of generating a methyl titanium bond. So, if you mix appropriate amounts of TiCl4 and Al2Me6, you will end up with METiCl3. So, while these compounds can be generated fairly easily, they are quite stable. The corresponding ethyl compound is not stable at all. So, you cannot make, using the same process, Ti ethyl group attached to the titanium. This corresponding compound is not stable at all. So, this needs a little bit of thought, because the initial understanding was that maybe the titanium transition metal alkyl bonds are weak, and it was only after the thermochemistry was carried out, it was realized that the metal carbon bond is not weak at all. In fact, it is quite stable. Here we have several bond energies pictured for us here. The metal carbon bond can be as high as 300 kilojoules per mole, and as I have told you earlier, if you go from titanium to zirconium, you have an increase, and you have two groups here which are pictured, and in both cases the bond strength turns out to be quite large. Tungsten, hexamethyl tungsten is in fact a special case, and we will discuss this little later if we have the chance to discuss the tungsten hexamethyl tungsten compound, which has got a fairly unique structure. So, the transition metal carbon bonds are not inherently weak, they are thermodynamically stable, and the instability is really coming from some kinetic factors. They have a reaction channel which allows them to decompose very readily. Now, since we are going to discuss this reaction fairly extensively later, I will only mention here that as long as you have a beta hydrogen on the carbon attached to the transition metal, you can have an elimination reaction that results in an alkene being formed. So, if you have a transition metal with an alkyl group which has got a beta hydrogen. So, this is the alpha hydrogen and this is the beta hydrogen, and this is a transition metal alkyl bond. If you have a beta hydrogen, then this beta hydrogen has a tendency to interact with the transition metal, and this interaction has been called the beta agostic interaction. You can also have in a few cases an alpha agostic interaction as pictured here, but this is much rarer than the beta agostic interaction that is pictured here. So, it is possible for the beta agostic interaction to lead to a decomposition reaction, and this can lead to a decomposition reaction in which the transition metal forms a olefin and a hydrogen. This is a reaction which we are going to discuss much later. But how do we know that this weak interaction is present in these compounds? Usually, you end up with unusual bond angles between carbon and hydrogen, and these unusual bond angles have been consistent with the interaction that we just talked about. So, short distances between the metal and the hydrogen. So, metal hydrogen short distances can be responsible for or can be used as evidences for these weak interactions. You also have NMR. In NMR, you can have this weak interaction can cause a different chemical shift, and it is also possible to have, if you have a crystal structure, you can see that MH distance is shorter than what you would expect. So, what makes them have weak interactions or agostic interactions? It is usually the deficiency in the electron count around the metal, and the CH bond is actually functioning as an electron donor. So, how do you avoid these agostic interactions? There seems to be only one way to avoid agostic interactions, and that is to avoid the beta hydrogen bond. And that is why very often one can form very strong metal alkyl complexes if you have no beta hydrogens. some examples are given here. It is not so difficult to generate them. You can have a CH2CF3. The CF bond is very strong and cannot be broken. So, if you do not want a beta hydrogen, you just replace them with fluorine or with methyl groups. So, here is an instance where the beta hydrogens have been replaced with a methyl group. You can also replace the beta methyl group, or in the alpha position you just replace the methyl group with a C6H5 moiety, then also you do not have a beta hydrogen. That is a benzyl group. And you can also have just a methyl on the transition metal. One very interesting way to avoid the beta hydrogen is to make it a bridgehead. So, you can have a transition metal which is coordinated to a bridgehead, and that is what we have shown in this particular instance. So, you can have zirconium with 4 carbonyl groups, and that forms a very stable moiety. And because you cannot form a double bond at a bridgehead, so you cannot form these bonds, it is difficult to form double bonds in the bridgehead, then it becomes unstable. So, transition metals complexes which have got a carbonyl group is quite stable, and you can observe them. So, what we have seen in this lecture today is a fact that metal alkyls are in fact quite strong, and you can make them fairly readily directly from an active CH bond containing organic compound, or you can use a CX bond to generate the metal alkyl species. Once you make the metal alkyl species using a very electropositive metal, and this turns out to be in this case lithium, magnesium or aluminum. So, if you have a very electropositive metal, you can use the CX bond or an active CH and generate a metal alkyl species, and then you can transfer them to a transition metal. So, from these electropositive elements, you can transfer the alkyl groups to the transition metal. And once you make them, you realize that you can have a reactivity that is dependent on the type of species they form. There are many instances where the species can be in what is called a Schlenk equilibrium. Especially in the case of Grignards, you can have a Schlenk equilibrium that changes the reactivity of the species. In general, the metal alkyl species, especially Grignards, can be stabilized with coordination of an ether molecule or an amine, and that makes them quite stable and less reactive. Metal alkyls occasionally generate radicals. They occasionally generate radicals, and so one has to watch out for radicals in solution, because the presence of radicals in turn initiates radical type reactions. We also discuss the bond strength variation in main group chemistry and in transition metal alkyls. We found that for transition metal alkyls, as you go down the group, the bond strength increases, whereas for main group elements, the bond strength of a metal alkyl moiety decreases. So, this anomalous behavior has to be kept in mind when you look at the chemistry of metal alkyl species. In the case of transition elements and their alkyl compounds, we have kinetic instability. This kinetic instability is because you have a beta hydrogen. We can have agoustic interactions of the beta hydrogen with the transition metal, and that in turn leads to instability or decomposition pathways, and so it is difficult to make transition metal alkyls with a beta hydrogen, unless they are having a saturated metal center. Lastly, we encountered this 3 center 2 electron bonding in many situations, and you can also have 3 center or a 4 center 2 electron bonding as well. So, 3 center 2 electron bonding and other interactions, complicated interactions tend to make the structures of metal alkyls fairly interesting from the theoretical standpoint. So, metal alkyls are fundamental in organometallic chemistry and are used extensively, and we will look at some of the chemistry in future lectures.